This is the third part and the last part of paper 4, May June 2023, paper 4 variant 1. Now the question C, we stopped at B before, but this is question C. The star in B is a distant galaxy. A spectral line in the light from this galaxy is known to have a wavelength of 486 nanometer. That's the spectral line in the light from the galaxy. So from the galaxy, we observe the wavelength to be 486 nanometer. The spectral line in the light from galaxy observed on the Earth, the one observed on the Earth is 492 nanometer. The one observed from this galaxy is 486. On the Earth is 492, as you can see. On the Earth is 492. From the galaxy is 486. So on the Earth, which is more longer, is higher than the one we observe on the Earth is much higher than the one from the galaxy. The first question said that explain why the wavelength observed on the Earth is different from the wavelength that the galaxy is known to be emitted. Now, this simple effect is known as Doppler redshift. Why? Because the one observed on the Earth is longer than the one observed in the galaxy. So our simple reason will be, it's 2 marks, that will be 2 points. So let me put it like this. The observed wavelength is longer, therefore the observed wavelength is longer, therefore the galaxy is receding. So into bracket, when the galaxy is receding, we call the effect Doppler redshift. When it's moving away, Doppler redshift. That's it. And the last question, we have to determine the value for the Hubble's constant. Okay, the 3-mark question. Now, from Hubble's law, we know that the receding velocity is proportional to the distance. So first, receding velocity is equal to Hubble's constant multiplied by distance, equation 1. Now, we need to get the value of velocity. And since what happened earlier is Doppler redshift, we have a general equation for Doppler redshift, that is change in lambda over lambda equal to change in frequency over frequency equal to velocity over c. We are going to treat this formula as if we are using sine rule in math. So you pick any two. So from here, we are only concerned about change in lambda over lambda equal to velocity over speed of light. Now, what's the original wavelength anyway? The original wavelength is the one observed from the galaxy, 486 nanometer. So what the change in wavelength? That will be 492 minus 486. They're all in nanometer. So change in wavelength is 6 nanometer. So substitute this value into this equation 3. Let me call this equation 2. Substitute the value in equation 3. So what's our change in wavelength? That's 6 nanometer. Original wavelength, that will be 486 nanometer. I'm looking for the value of velocity, but c, the speed of light, is 3 times 10 to the power 8. Nanometer cancel nanometer, cross multiply. When you cross multiply and make v the subject of formula, so v will be 6 times 3 times 10 to the power 8 divided by 486. So what's our v now? So when you divide 6 times 3 times 10 to the power 8 over this, we should have something like 3703703. In standard form, that's 3.7 times 10 to the power 6 meters per second. That's the value of velocity. But the question asks us to find the Hubble's constant. So from equation 1, make Hubble's constant the subject of the formula. That will be v over d. Hence, Hubble's constant will be our v is 3703703. The distance, what's our distance? 1.8. It's given in the question above. 1.8 times 10 to the power 24. Okay, make use of your calc. 3703703 divided by 1.8 times 10 to the power 24. At the end of the day, we have the value of Hubble's constant to be 2.06 times 10 to the power minus 18. The unit for Hubble's constant in this case is per second. Thank you. This is the last question. My next video will be on paper 4 mechanics 2023. See you shortly.